work I first learned about almost 30 years ago, almost the dawn of time for me. And, so the title of my talk is Subscheme Methods for Nodal Curves. Started. So introduction. So let's begin in a very classical setting. A lot of classical algebraic geometry is involved in the study of a single smooth curve, typically often over the complex numbers. In more modern times, our perspective has changed somewhat. We've become more, because of our success, I guess, or the success of others, we've become greedier and want to study simultaneously all the curves of a given genus and families of such. And for this, it essentially is sufficient to study one family. There's a single family or stack, or known as we call MG, the modular space of smooth curves of genus G. But if our focus is on global, especially enumerative results, we need to work with a compact space, so we need to compactify it, and one generally works with the standard compactification, which is the MG bar. That's a Riemann compactification, which is the parameter space for stable curves, meaning nodal curves with a finite automorphism. And then the study of the single MG bar is equivalent essentially to studying simultaneously all families of stable curves. Okay, now what about methods for studying these objects? The classical method as long as you're interested in a single smooth curve is to study divisors on X, or what is the same thing, essentially finite subschemes or line bundles. All those things are equivalent to each other. But when it comes to MG bar, you're studying singular curves. Actually, the contemporary theory in the contemporary study of MG bar, it's much more common nowadays to use a completely different tool, an extrinsic tool, which people call Roman-Witten theory, which is the study of modular spaces of maps from your curves to some other varieties, such as Pn, or say Calabi-Yau manifold, or something like that. So the work that I want to talk about here its purpose is to adapt these very classical divisor methods that we normally use for smooth curves or single smooth curves in the setting, in this more general setting of stable curves. And notice now, it's a very basic fact of life, that as soon as we have a singular curves, ideals or subschemes are not any longer locally principal always. So if you're going to try to work with a compact, complete parameter space, you have to work with subschemes rather than invertible sheaves. You have to have something with a geometric meaning. I mean, it's possible to work with invertible sheaves, and I guess some people have tried, but it seems if you want to work with subschemes and equations and things like projective geometry, which is what this conference is about, you have to work with ideals, and therefore that leads to the next thing. So I want to introduce this concept of smudgy curves. What are they? And their moduli space or stack. So this parameterizes pairs consisting of, firstly, a nodal curve of genus G, arithmetic genus G, together with an arbitrary subscheme of length m, such that the automorphisms of X fixing Z are finite. So the curve X is a nodal curve. It's not automatically stable, but its lack of stability is sort of easy to understand. Just there have to be at least a length 3 special amount of material on each rational curve. Okay, so this smudgy approach is, you might consider some kind of intrinsic counterpart or analog, in some sense, of the extrinsic Gromov-Witten theory. In some sense, because you're working inside the curve, you might expect that this object is easier to understand than trying to map this curve into something else. So working with this space of smudgy curve, you can work one family at a time, so to speak. And then there, what we want to study is the relative Hilbert scheme of a given family. Okay, so that leads us to the Hilbert scheme. So let's start with a nice family of nodal curves. Its fibers are all nodal curves of fixed genus G. And in this, we may assume, if you like, that the total space is smooth. Doesn't make a big difference. Now, to this we can standard construction associated with the relative Hilbert scheme of degree m, which is itself spaced over V. It parameterizes pair consisting of a fiber plus a length n subscheme of that fiber. And it has the standard universal property that it represents for every scheme the set of all diagrams where you have a base change of the given family over this S and the subscheme of the base change relative curve. And there, again, another standard thing that comes with having the Hilbert scheme is that there is a universal subscheme, which is a subscheme of the product of the Hilbert scheme with the given family. And also there is a tautological, there are these tautological bundles that we can construct, that is, starting with any given vector bundle on X, we can form tautological bundles, which I denote by lambda sub m of L, having rank m times rank of L on this Hilbert scheme, and the fiber of this bundle on a given point of the Hilbert scheme, that is, on a given scheme, can be identified with the restriction of the bundle on that subscheme. Okay, what typically happens that in applications of the Hilbert scheme to geometry, what you're actually working with are going to be these tautological bundles associated to various vector bundles, or even just the canonical bundle. So here is as a sort of a classical example, you can consider the relative dualizing sheaf of the family, the relative canonical bundle, and its direct image over the base, which is called the Hodge bundle. And then if you're working over the Hilbert scheme, there is this fundamental map going from the pullback of the Hodge bundle to the mth tautological bundle associated to the canonical bundle, which simply takes a global differential and restricts it on a subscheme, on a collection of points, to speak. Now, this is especially important because essentially the Riemann-Roch theorem, for a smooth curve anyway, tells you that the locus where this map I call the Brill-Noether map, this map drops rank by a given amount, say R, is precisely, since we're working on the smooth curve, subscheme is the same thing as a divisor, there's an associated linear system. So the locus where the map drops rank by an amount of R is precisely the locus where the linear system has dimension at least R plus 1. And in some very famous classical work from the 1970s by Kemp, Kleinman, and Laxov, they use this setting, this mapping, and properties of some computations involved with this mapping and Chern classes and so on to prove the existence of special dividers. I need some help here. Sorry about that. Sorry. Did I do something?
Sorry. Don't wait. Just you have to wait.
now we're going to study the Hilbert scheme, and sort of an obvious approach to studying it is to relate it to something, in some sense, much simpler. That is the relative symmetric product of the curve, which, well, it's in some sense simpler, although it's highly singular. So, what are some basic results about Hilbert and this mapping, the so-called?
Yes.
Yes. Close it.
Yes.
Okay. So this is called a Hilbert to seam or cycle map, going from the Hilbert scheme to the symmetric product. So we basically want to analyze this map, or how much difference there is in the Hilbert scheme compared to the symmetric product. So some basic results on the Hilbert scheme and on this map are the following. First is that unlike the symmetric product, the Hilbert scheme is what you might call virtually smooth, in the sense that if the total space of the original family is smooth, then so is the total space of this relative Hilbert scheme. On the other hand, the relative symmetric product is these horrible singularities, really bad singularities. Well, they're quotient singularities, but they're really bad. So you might say that the stack, the smudgy stack, is actually a smooth stack. Moreover, actually, the structure of this map C sub m, the cycle map on the Hilbert scheme, is what can be described in great detail. In particular, what's true is that this map is a small blow-up. Its exceptional locus is supported over the cycles that have multiplicity at least 2 over the nodes. And in fact, you can describe it as the blow-up of a non-Cartier divisor, of a Weil divisor, a specific Weil divisor, in fact, the so-called discriminant locus, which parameterizes all the non-reduced cycles that have a multiplicity at least 2 some. So yeah, so it's this small block. In fact, it's already interesting in the case m equals 2, where the map C2 is this Francia flip block. For example, we can explicitly describe its fibers. For example, in some sense, the worst fiber, the most singular, over the most singular cycle, that is a cycle totally concentrated at a node, it has this nice description as a chain of P1s. Well, I think it's hard. Well, I haven't figured out how to do it in tech. Just do it on the board. So there are these fibers, CM1, CM2. They are P1s. They are nice P1s. So on up to CM minus 1. All of them are P1s, and as you can see there, they can be described completely explicitly as families of ideals, almost all of which are locally principal, and only at these nodes, nodes n is the endpoints here of this chain, you get non-principal ideals. And in fact, it is these parameters, these A's, one for each P1, they constitute essentially the extra information that you have in the Hilbert scheme relative to the symmetric problem. So one thing that you can get from this is that there's this sort of new Cartier divisor on the Hilbert scheme that was very far from Cartier downstairs. You pull back the discriminant, it becomes divisible by 2 as a class, not as an effective divisor, but as a class. So there's this line bundle on the Hilbert scheme, which I like to call the discriminant polarization, and that turns out to be an essential element of the study of the Hilbert scheme. Aside from that, the main new cycle or geometric object in the Hilbert scheme that wasn't present in the symmetric product are what I like to call node scrolls or polyscrolls, which generalize these C's that appears here. They're basically bundles of these C's. So to describe them in a little more detail, let's fix some data. So a collection of nodes, the relative nodes. So they're not points, but they're sections, each one defined over a boundary component. And they will be defined simultaneously over the intersection of these boundary components. And we give ourselves multiplicities, one associated to each node, and a type. So a type is the subscript of these. Corresponding to the subscript in the C here. And then we can consider the partially normalized family, boundary family, corresponding to this collection of nodes. So they're in the original family of this subfamily of multi-curves having these R many nodes or more, and you blow up at these nodes, you get a new family which is generically smooth at these, well, generically smooth of lower genus, right? And okay, and then we have this this P1 to the R bundle, which I denote by this F with this other decoration. It is a P1 to the R bundle over what? Over the Hilbert scheme of this lower degree. Associated to this lower genus curve. So it is, in some sense, something. This family here on the right is, in some sense, something. It's a simpler Hilbert scheme, in at least a couple of ways. And this thing forms a bundle over that, P1 to the R bundle. And one of the main results that I have, enumerative results that I have, is a complete description of this bundle. So let me describe that in the case of a single, not a polyscroll, in case R equals 1, we have just a P1 bundle. So how do we describe that? So the family, this new boundary family that we get in that case will have a pair of distinguished sections, call them the theta x and theta y, and therefore the base of that family is going to be endowed with a couple of line bundles. They're kind of standard in the study of MG bar, the cotangent classes psi x and psi y, which are just the pullbacks of the cotangents at the two branches. And so now we have the following theorem, a structure theorem for these node scrolls. It tells you that this node scroll is, well, it tells exactly what it is. It is the projectivization of this very simple rank 2 vector bundle, a direct sum of two explicit line bundles, which there you see are linear combinations of these standard classes, the cotangent classes. Okay, so the second on the second line there of the description of D, this well, there's this theta x, which itself is a line bundle, and it induces a line bundle on actually already on the symmetric product, and therefore certainly on the Hilbert scheme. So this is this m minus n star is the induced line bundle on the Hilbert scheme, and then the last one is just the discriminant on this smaller Hilbert scheme. So we can give a complete and explicit description of this Hilbert scheme in terms of this sort of elementary vector bundle on the right. And what's important is that this isomorphism is not a mere isomorphism, but what I call a polarized isomorphism, in the sense that on the left, this F thing is a subvariety of, not exactly a subvariety, but it's a normalization. It's a desingularization of a subvariety of the Hilbert scheme of degree m. It carries with it the polarization induced by this gamma m. So the left is polarized, and the right is polarized in the standard by the standard O of 1 induced by the vector bundle, and the two agree. It's the same polarization. That's important. Okay, so now one major goal of studying this Hilbert scheme is to do intersection theory on it. That's why one of the main reasons why we want a global compact space. It's compact as well as smooth. And now, so the important, for enumerative geometry, the important classes on the Hilbert scheme are the Chern classes of the tautological bundle associated in general to some vector bundle lengths. And the numbers that have important geometric meaning are going to be Chern polynomials of these bundles there. In general, there will be polynomials in these Chern classes. So the objective then is to compute all polynomials in some sense, not just those of top degree, but all polynomials in the Chern classes. So the idea as to how to go about it is sort of a very standard idea in intersection theory is to try to use induction, an induction on M, on the degree of the Hilbert scheme in question. And that kind of induction typically, again, I think it's a standard idea. You want to use the flag Hilbert scheme that parameterizes pairs of two subschemes, one of length m-1 and one of length m. So this is what we call the flag Hilbert scheme, xm m-1. And it is endowed with three maps. So by definition, it maps to xm and to xm-1. It turns out there's then a third map, it's a morphism to kind of the last point. There's a m-1 part, and there's a big one, whole thing, and then there's a remaining residual point or something where they have a morphism to x. Okay, so, and then another, again, pretty standard, well, it's an analog of some standard results in section theory, is that the big advantage of working on this flag Hilbert scheme is that there is this decomposition of the Chern class. If you go up to the flag Hilbert scheme, which is, by the way, the map PM is a generically finite map. So pulling back doesn't change much. Anyway, so if you go back to this flag Hilbert scheme, you can factor the Chern class of this tautological bundle into what? Into the analogous thing of degree m-1 times some rather relatively simple object which involves the gammas. So this discriminant degree m, well, minus, if you like, the opposite sign, the discriminant degree m-1. And what that divisor there inside of that we're twisting by means is that it is the locus of points of schemes, I should say, where the last point coincides with one of the m-1 points before. Right? So we have this simple decomposition here, and this leads one to try to approach this program of computing intersection numbers in the following way. So, I mean, if you know stuff, so the general idea is if you can assume recursively that everything you could possibly want is good in dimension degree, Hilbert degree m-1, and then you want to go over to the next degree. So what does that involve? What new difficulties does that involve? Well, there's this gamma m-1 part. Well, that's already also of degree m-1, so that's not going to be a problem. The new thing is that you have to take the stuff that you had in degree m-1 and multiply it by this, in general, a power of gamma m. Right? So one is led to the following program. So there's two steps. First of all, you want to define an appropriate well, I call it the tautological module. It's a priori an additive thing. Well, it is an additive thing. It's an additive group with certain generators. So, well, it also admits you can multiply by things coming from the base x. These are kind of innocuous. And in general, so the generators for these what I call the discriminant module, the logical module, it's the same thing eventually. So first of all, you have all kinds of diagonal cycles. So you have a product, symmetric product. There are naturally some diagonal cycles where you give us a partition and then insist that within the given blocks all points should be the same, should coincide. So for every partition you get a cycle, and that gives you, that's one of those generators of the logical module. For example, one of them would be the polarization itself. It's just like twice a point plus m minus 2 other points. Okay? So it's the partition, I don't know what you want to call it, 2, 1, and 1s. Right? That's one kind. And in general, there are other such cycles of various codimensions, all the way down to the small diagonal. All points are the same. And then the other type of generators are the node scrolls, I described before, and polyscrolls in general. And then you can also have to admit sections of them by the polarization. So that's f dot gamma. And of course, all various twists of those corresponding to classes coming from the base x. So this is what I call the tautological module. And then one of the main results is the tautological module. Theorem about the tautological module is the following fact, that via intersection product, this tautological module is a module over the polynomial ring in gamma m, in the sense that given one of these three types of classes, you can multiply it by gamma, the power of gamma, and you can write down the result, in fact, explicitly with some explicit coefficients, as a linear combination of the other classes. So, for example, if you look at one of these small diagonal cycles multiplied by the polarization, then this product can be expressed as a linear combination of what? Of diagonals and of node scrolls. So let me point out that this intersection that is featured here is very far from a proper intersection. In fact, the gamma mu is a subscheme. It's a subscheme of gamma upper n. So it's a non-proper intersection. The result is that it is there are certain obvious other diagonals that appear in the intersection, and there are some not so obvious things that appear, and these are some node scrolls, and they appear with certain coefficients, which are still a little bit mysterious to me. And another special case of this is you can always multiply 1, keep multiplying it 1 by gamma m, and you can write down the result in terms of those generators. So every power of the polarization is an explicit linear combination of those generators. So that's one thing, that's one step, and then the second step, and it's motivated by this splitting principle that's said here. You have to know how to relate things in degree m minus 1 and things in degree m, and formally they're related by this transfer map. So the result is that there is a transfer map in the understanding of the tautological model. So you can sort of carry over one of these generators over to from degree m to degree m minus 1, pull back and push forward, and the result is still a linear combination of analogous generators. Not only that, in fact, with explicit in an explicit sense, with explicit coefficients. So one can write this down, and then, as I already alluded to, if you combine this transfer result with the fact about discriminant modules, together with these two, you can compute any polynomial in this Chern classes of the topological bundle. So in some sense, at least in principle, we can completely understand the intersection theory of this relative Hilbert scheme. And yeah, like I said, well, that's one kind of, I think, one way in which this Hilbert scheme approach is advantageous, has advantage over this Gromov-Witten stuff. The spaces, the Hilbert schemes are ultimately quite a bit simpler than this Gromov-Witten, this moduli of stable maps. They don't have this extra large dimension and stuff like that. And the intersection theory is ultimately relatively tractable, I think. Not somewhat unlike in the Gromov-Witten setting. Okay, so let me now describe some applications, which are at least in part work in progress. So the applications are to what we call modular subvarieties. So we want to consider some subvarieties of this Smudgy moduli space, as well as their images down in the ordinary moduli space. And then the problem is to compute the fundamental class of let's say, the image in the moduli space, mg bar. Or in some cases, if it has extra large dimension, we're going to compute the virtual fundamental class. But actually, in many interesting cases, you don't really need to go virtual. It's actually the thing actually has the right dimension, and you really want to compute the actual fundamental class. And generally, one wants to do that in the setting of the Mumford ring, which is generated by the kappa classes that he introduced. And an obvious example of this, related to what I described early on, is the closure of the locus of smooth curve carrying a GRD for a given R and D. And an even much more special case that, well, to me anyway, is quite challenging, is just to look at the locus of hyperelliptic curves, R equal 1 and D equals 2. So that is, well, in some sense, it's very, very concrete and explicit and simple, but on the other hand, it does have high codimension in moduli. So this issue, this business of MRGD in computing its fundamental class has a long history, especially in the case where it has codimension 1, where it was subject to a great deal of deep work by Mumford, Harris, Eisenblatt, and many others. And there's a lot known in that case, in the divisor case, but much less is known beyond that. So one possible potential application of this theory of Hilbert schemes is to this thing for high codimension. So I want to now focus on the case of the closure of the hyperelliptic locus. And the starting point here is, of course, the Brill-Nerthen map of degree 2. The map, the bundles in question, and the map all extend without any problem over the compact thing, the Smudgy M bar G2. So there's no problem to extend it. Yeah, and so there we use the tautological bundle associated with degree 2, associated to the canonical, relative canonical. Now, as long as you are working on the interior of a smooth curve, if you look at the determinantal locus, D2 of E, that is where the 2 by 2 minors of the matrix in any local basis vanish, this is the same as the so-called 2-point hyperelliptic locus consisting of a hyperelliptic curve together with a point in the hyperelliptic, a pair, I should say, in the hyperelliptic system. But as soon as you go to the boundary, this is very far from true. This map is, in some sense, quite poorly behaved. It's much more degenerate than you would like it to be. So let's analyze this a little bit. Now, the boundary breaks up as the delta 0 part and delta plus, where delta 0 is the closure of the locus of irreducible one nodal curve, and delta I is the locus of curves of the form curves of genus I, union curve of genus G minus I, meeting at a point. And let's look first at the easy part, this delta plus. A little more detail. So these curves in delta plus, the way I like to look at them is that they have this point, this node theta is what we call a separating node. Right, so this is curve of genus I, curve of genus G minus I, and this point here is a separating node in the sense that if you either remove it or blow it up, you have a disconnected curve, and the curve has two components, which I like to call a left and a right side associated to this node. And now in this situation, it is well known which of these curves of this type are limits of smooth hyperelliptic curve. This is the case precisely when either side, left or right, is itself a hyperelliptic curve, and the node is a Weierstrass point such that twice it is in the hyperelliptic system. And now, so that's on one side. On the other hand, when does the Brillouin-Noether map drop rank? Well, it always drops rank in this situation on the locus of subschemes that have 1 point or more in theta. And then, additionally, if one of these two curves or the other is hyperelliptic, then it's also going to drop rank on the hyperelliptic pairs on one side or the other. And then that's not a good thing, because in general, if only one side is hyperelliptic, you don't want it to drop rank. So you want to change. You have a quantifier problem where you need to convert the or to and. Okay, so now let's see how we want to go about doing that. So if we work, let's say, I shouldn't say delta 0 here, I should say delta plus. Sorry, that's a misprint here. So the Hodge bundle over the boundary, and also in the neighborhood, you can say in the neighborhood of the boundary, will split into a left and a right side corresponding to the left and the right curve, where the sections on the left side vanish on the right and vice versa, identically. And then it turns out that's not quite enough. You have to go a little further and look at even smaller subbundles consisting of sections that actually vanish twice on the opposite side. So the strategy is to modify, to do a birational modification of the Hodge bundle, so as to, I mean, these sections that vanish identically on one side or the other, they are somehow, they're kind of the root of the problem. And we want to modify the bundle in such a way that it will, in one sense or other, bring those dead sections back to life. And we do that by enlarging. We want to enlarge the bundle birationally on suitable divisors. We can only do this on divisors. Now, what are the divisors we want to work with? Well, we have divisors in the Hilbert scheme. The relevant divisors, it turns out, are the locus of schemes which are entirely on the right side or entirely on the left side. And what you can do then is to do the so-called elementary modification of the Hodge bundle over the Hilbert scheme, pull back over the Hilbert scheme, corresponding to either the left side, the left side and the right side. It doesn't matter which order you do it, because the two are in general position. And that means that you are basically untwisting the EL. So sections in EL vanish identically on the right, so you're essentially untwisting them by the right side. You are you are kind of factoring out the equation on the right side from those sections on the bundle, over on the bundle side, and likewise on the other side. And that's not enough to do it once; you have to do it twice, and then at the end of the day, you get a new bundle called E plus, and because you did this factoring in the right way, the Brill-Noether map on E. So this is a larger bundle; it's a bigger bundle than the original E. Birationally, it's the same, but it's a bigger bundle, and the Brill-Noether map extends because you essentially divide it out by things where the Brill-Noether map vanishes. So the new bundle, I mean, the Brill-Noether extends to the larger bundle, and in fact, this does in fact trim down your degeneracy locus. At least in this nice case where, let's say, you have smooth curves on either side. In other words, you are off of delta. Well, actually, you don't have to assume that. You just have to assume that you are not you're not on delta zero. You're off of delta zero. Then the degeneracy locus of this new map consists of the good part, the closure, the genuine closure of the hyperelliptics, and as I mentioned, we know exactly what that is. And then there's still some part that's some sticky part that you don't get rid of in this fashion, but it's easy to understand. It's the locus of subschemes that are entirely supported in this node. So it's this scheme that is just this node with some tangent right there, and there's a P1 of tangent directions with a node, which all of them give you different subschemes. They have this locus R theta, which is a kind of P1 bundle, and then this plus the good stuff is the degeneracy locus, and then that's basically good enough for computing the fundamental class, because the thing on the left, the fundamental class, the virtual fundamental class, so-called, the thing on the left is computed by the Porteous formula. And, well, there's the Porteous formula, which is just some purely formal function of the bundles in question. And you can apply this to this map P plus, and you get some expression. And then this residual intersection theory of Fulton and McPherson tells you that this is equal to the good part, the closure of the hyperelliptics, which is itself a correct dimension, plus a computable contribution from this locus R theta. Because, I mean, well, this is sufficiently easy to understand that we can work with it and figure out the contribution to the fundamental class, and then just subtracting that part gives us the fundamental class of the hyperelliptics. However, this only works up to delta zero, like modulo stuff that comes from delta zero. And then the next step, which involves more work, and as I said, still to some extent work in progress, is to deal with delta zero. The closure of the irreducible curves. Now, so delta zero is the closure of the irreducibles. The irreducible curves themselves are not a problem in this setting. It is the reducible curves, which are in lower dimension, higher codimension in delta zero. It's there that the problem lies. And specifically, the difficulty comes from what I would call a properly separating binomial. I think that's written up there, right? Yeah, okay. And what's the picture? So you have two curves and they intersect like this. So you have a pair of nodes, neither one of which separates, but a pair of them do. And that's in the closure of delta zero. I mean, yeah, it's in delta zero. It's in the closure of the irreducible node curves, but it's not in delta plus or anything like that. So it's these kinds of curves are kind of the essence of the extra difficulty with delta zero. And so in a nutshell, why is that? So again, what happens here is that the curve splits into a left and a right part. They're separated by the pair, not by any single node. And let's assume that either side is irreducible. Again, so you can write it on the canonical in the obvious way, and then also the Hodge bundle splits. Now the problem is that in this situation, the dual additive is never very ample, so you always have some degeneracy for the map phi. Or even if you modify it for the delta plus, it doesn't help here at all. It still drops rank always, for any curve at all. So you want to, again, try to play the game of enlarging the Hodge bundle so as to reduce its degeneracy. On the other hand, of course, this kind of curve is not always a limit hyperelliptic one. It's easy to analyze when it is. It's precisely when the two sides are hyperelliptic, meeting in hyperelliptic pair. And then, so we want to modify the Hodge bundle. So the problem now is, which didn't occur in the separating node case, is that the difficulty occurs in a codimension 2 locus and not codimension 1, whereas the bundle modifications is a codimension 1 construction, divisorial construction. So the obvious answer to this is to blow up. And then the question is, why do you blow up? Well, you want to blow up the locus where the map is 0. So they are, the natural thing to believe is that they are again the locus of subschemes which are entirely on the left or the right side, and indeed you can blow them up, and you get two new divisors, and there's a blown up space here, which I call it azimuthal Hilbert scheme, which let's say associated in this case to this particular node. And indeed, now, so once you do that, in fact, you can play a pretty similar game. You can do this twisting by this divisor, and you get a new bundle, a larger bundle, and the map, the Berliner map extends to this larger bundle again, and what happens is that for this new bundle, if you want to analyze the degeneracy locus of this phi plus, it essentially corresponds to looking at 3 different linear systems on this reducible curves, which was those I wrote there, and the map will drop rank even only in the case where you have sort of degeneracy in all 3 of them simultaneously. And it's easy to analyze. This happens precisely in the right case where you really have 2 hyperelliptic curves meeting in the right kind of pair. So that essentially takes care of the case that you have a single separating binode, but then it's sort of a feature of the difficulty of delta node that's not good enough, and you have to deal with general configurations of binodes. In general, they will not be disjoint. I mean, so you're okay as long as you have disjoint binodes, but if you have binodes which have a point in common, then it gets more complicated. Well, also more interesting, I guess. So you have, in general, what you need to deal with are cycles of nodes, what I call polyseparators. So there are cycles, there are kind of cycles of nodes where every pair of them is no single one is a separator. Every pair of them is a separator. So that's what I call polyseparator. And then there is a way to do a blow up. There's this kind of scheme. I think a nice scheme to blow up these loci. So these loci so one-sided the schemes in this configuration, all on one side of one binode or another. They're not in general position if you look at different binodes. They intersect in the wrong dimension, but they are still, I think there's a word for this, it's called quasi-transversal or something. They don't intersect in the right dimension, but they still have a nice enough intersection of the wrong dimension. So it is possible to define a scheme, a nice scheme to blow it up, which gives you a smooth space, or at But this it's nice in the sense that it's smooth. The blow-up is smooth. And it's also possible to analyze the exceptional divisors. At least in principle, it's possible to analyze the exceptional divisors in their intersection theory in a reasonable way. And then ultimately, then you get modified Hodge-Gundel and well, hopefully, so this is to some extent it's a work in progress. So for this, when you do this modification for all the binodes and all these poly separators and stuff, you get this new bundle and the map, this polynomial map, and in the degeneracy locus consists of the right stuff, the closure of calculatrix plus this sort of relatively innocuous part, this all the sum of the r thetas coming from the separating nodes, and then this can be analyzed and you can compute the fundamental